Good morning, everyone. I am Julien Duron, and I will talk about adjacency labeling scheme for small classes. This is a joint work with Edouard Bonnet, my advisor, John Sylvester and Victor Zamarev from Liverpool. And I would like to acknowledge Maxime Zukovsky for a nice idea. Yes. So here is a picture of my colleague, and let's dive into the topic. So instead of adjacency labeling scheme, I will first introduce universal graphs, but it's the same thing, just an easier point of view. So imagine you have a set S of graphs, and you want to find a universal graph. So it's a graph that contains each graph of S as a induced subgraph. So here, the graph at the bottom, you can check that it contains indeed the click, the cycle, the star, and the bus as induced subgraphs. Okay? And this is equivalent to a bit more complicated definition of labeling schemes. So given the same set of graphs, a labeling scheme for this set is a choice of label for each vertex of each graph. It's this function that takes a vertex V and output a word of bits. And an algorithm that given only two labels between two vertices needs for two vertices needs to return if there is an edge or not between these two vertices. So let me explain why these two notions are the same. So what we can do actually is, given a f of n adjacency labeling scheme, we can build to the f of n universal graph. And given a universal graph, we can build a labeling scheme. So how does that work? The idea is, if you have a universal graph, then you can enumerate its vertices and so give them a label. This will need log of the size of u bits for each label. And then for each graph in S, you can just look at the labels in your graph U and give the same labels to the graph of the graph U, the vertices you choose. So for example, here you have the labels 0, 0, 0, 0, 0, 1, 1, 0, 0, and 1, 0, 1 for the click. Okay. So in this talk, instead of looking just at the universal graph of sets of graph, we will look at universal graph of classes, in particular infinite classes. And instead of defining them on the infinite set, what we do is we divide the class into levels. So C is divided into the Cn, and Cn contains only the graph on n vertices. And what we ask for is a universal graph for each of the Cn. So here is the graph Un that is universal for Cn. And equivalently, this is finding a representation for each of the Cn. And the main topic, the main goal in this topic is finding universal graphs and universal sequences as small as possible. Okay. So let's have an example. Consider the degenerate graphs. So a graph is degenerate if you can find an order on its vertices. Here it's the order v1, vn, such that a vertex vi has at most v neighbors in the set of larger vertices, or in g of y plus 1 vn. So this is a strong property, but it contains a lot of classes, for example, planar classes. And what we can do, so we want to find the adjacency labeling scheme, is for each vertex vi, you can give VI the label order of VI, place of VI in the order, followed by the place in the order of each neighbor of VI that is larger than it. And we know there is at most B of them. Since the place in an order can be encoded in log of n bits, this gives you a label of size d plus 1 times log n. And then you want to decode this label. So you take two vertices, you know that there's a label, and your algorithm will output yes if at least one of the vertices is contained in the set of labels of the other users. So here, does V1 is in the set of U1 WD or Vj is in W1 WD. And you can check that it's indeed a labeling scheme. So this gives you a labeling scheme of size d plus 1 times log n bits, with d plus 1 log n bits for each label. Okay. There is a second notion to this talk, is the speed of classes. Consider a set of class of graphs C, then the speed of C is just the map that gives the size of each level in the class C. So in general, it's not very useful. You could, given some function for the speed, you could design whatever the class you want by just taking this number of graphs on each level. It's not very constraining, but when you look at hereditary classes, it's suddenly very useful. And I'm sure from now on, we will only look at hereditary classes. So I will try to explain why it's so useful on hereditary classes. The main idea is add a large number of constraints, large constraints, sorry, on the possible speed you may have. So for example, now it is theorem of Alesker and Bolubash and Thomason that states that the limit of the speed always exists for hereditary classes. So it's not exactly the limit because it's usually infinite. So it's the logarithm of the speed divided by n plus 2. And this limit always exists, and it cannot take any value. It takes value in the following thing. So it's quite surprising. We have some constraint as soon as the class is hereditary, but actually there is even more powerful constraints. At least more interesting for us. It's when you look at small speeds, the following happens. It's a theorem of Scheinerman and Zito. So either your class has a constant speed, so you can imagine the class of clicks. Each level has size 1 and it's indeed hereditary. Otherwise, you may have a polynomial size for each level, an exponential size, a factorial size, or a superfactorial size. And the idea is there is nothing in between. So constant, polynomial, and exponential, they are well-characterized classes. But factorial classes, they are super general. So the question is, well, is there some characterization of factorial of this factorial layer? And it's the subject of the rest of the talk. Just for completeness, let's have a look at some classes of factorial speed. So as we said, there is a planar graphs and in general bounded degeneracy. So you can just count how many ways you have to have an order on the graph and a bounded number of larger neighbors. And you can also find a way more general class of bounded symmetric difference that contain twin widths, liquids, fluids, proper mind of yours, etc. But actually, there is way more classes than those ones. Why have we talked about these two notions? It's because there is a strong link between them. The link is the following. If you have a large speed, you cannot hope for a labeling scheme with small labels. This goes as follows. Imagine you have a labeling scheme with only g of n bits for each label. Then for each graph, you can just concatenate the labels, say in lexicographic order, and this gives you a unique word of letters for each graph. And two graphs cannot have the same word, otherwise they would be equal. And so since there is at most 2 to the n times g of n different words and n times g of n bits, there is at most this number of graphs. And immediately this gives you that n times g of n is at least the logarithm of the size of the level, nth level. Okay? And this gives rise to the following definition. We say that a class has an implicit representation if it admits a labeling scheme that is almost optimal. So it would be optimal if it would achieve the previous bound, but here we are happy with a constant factor from the optimal bound. And this definition, it gave rise to one of the most important conjecture of the field, is the following. The implicit graph conjecture. So if you have an hereditary and factorial class, then the conjecture was that it admits an implicit representation. Just if you plug in the previous bound with the constraint on factorial classes, you will end up with this O of eigenbit labeling scheme. This is just an application of the previous theorem. And it was open for 30 years, but it was disproved 3 years ago by Hoya and Ahmed Atami. And they not just disprove the conjecture, they show that there is actually an exponential gap between what was stated in the conjecture and the truth. They show that there is hereditary classes that are factorial and need at least 4 of root of n bits in their labels. And this proof, it's a very nice proof by probabilistic method. The idea is to count the number of hereditary and factorial classes on one side, and to count the number of universal graphs on the other side, and to compare these numbers to find some bounds. And so it gives rise to 2 open problems. The first is this root of n tight? So we know we can have O of n by looking at the adjacency matrix, for example. But we don't know if the right bound is root of n, or something in between. The second open question is, okay, it's false to ask implicit representation in general for factorial classes, but what would be a class that admits an implicit representation among the hereditary and factorial classes? This is the subject of our contribution. So we look at small classes, which are the restriction on factorial classes. So a class is small if it has speed at most some exponential times a factorial. And the idea is it's way smaller than factorial classes, but it still contains a lot of the class we used to work with in daily life. Typically a minor clause, bounded with its stuff like that, but not bounded determinism. And so what we prove is actually if you ask for a small class instead of a factorial one, in the world of weakly sparse graphs, so KTT3, so graph 3, then you have an implicit representation. And the second theorem is, even in general, we don't have yet at least O of log cube of O of log n bit labeling scheme, but we prove that there is O of log cube of n bit labeling scheme. So the lower bound of O of root of n is way smaller, at least for small classes. So I will try to give you an idea of how we proved those results. So let's attack the first one. We want to prove that if you take a small class that is sparse, then it has an implicit representation. And actually, you can ask for a weaker statement. Instead of asking for a small hereditary and sparse class, you can just ask for a monotone class that is small. Because being monotone forbids you any possible KTT free already, and it implies being hereditary. And this was a theorem we proved with Maxime before this paper. The proof is not too hard. It goes as follows. Imagine you have a class that is both monotone and small, then it's small for some constancy. And actually what we prove is something super powerful, is that the class is not just monotone and small, it's degenerate also. So this directly implies that we have a Laplace scheme because we found a Laplace scheme for degenerate classes before in the talk. Well, we saw it. So how does the proof go? Imagine you have a graph H that has a very large minimal degree in your class. Actually, you can prove that if you have such a graph H, you have also a graph that has both large minimal degree and that is spanned by a tree of bounded maximal degree. The 2 degrees are. So why is it useful? It's because when you want to build a lot of graphs in your class from this, what we do is we build a lot of graphs in your class from this graph H. How do we do that? We say the following. Suppose you have some graph F that contains T and that is contained in H. Then your graph F, it doesn't have many automorphisms. Why is that? It's because there is no many ways to embed T into H. And so in particular, no many ways to embed T into F. And so this bounds the number of automorphisms of F. And then it's just a brute force computation. You take the size of the class. This is at least the number of subgraphs you can make from H. And this is at least the number of subgraphs F of H, sorry, that contains T. But since you may end up with the same graph sometimes, you need to divide by the automorphisms, the number of automorphisms. And then it's just a simple computation. How many graphs, how many subgraphs of H contains T, and how many automorphisms there is of T. And this gives you a bound that is way larger than what the small assumption gave you, which is a confirmation. So this gives you a proof that if your monotone is small, you are degenerate. And we want to use it in the hereditary and sparse case. How does it work? The idea is we will ask for we will actually ask the same. So we will prove that the class is degenerate, but for a much larger D. And this minimum degree actually is sufficiently large to allow us to use a theorem of Kuhn and Ostus. That is the following. If you have a graph G that has sufficiently large minimum degree and that is sparse, then you can find an inducible of H that is actually a one subdivision of a graph H prime of large minimal degree. Okay, so it's a bit of strange statement, but it's super powerful because when you look at the monotone closure of H, it's super close to the hereditary closure of H, because removing the subdivided vertex on each edge allows you to remove edges of H prime. And so by looking at the hereditary closure of H, we can mimic the proof we had before for monotone classes. Okay. I would like to briefly talk about the second proof also. So how can you find a labeling scheme with O of log n to the cube bits? The idea is a bit more tricky. We will need two tools. They are neighborhood complexity and contiguity, but I will just briefly talk about them. Neighborhood complexity is a concept that is very close to DC density. And contiguity, we can define it in the following way. It asks if there is an order in the vertices of the graph such that the neighbor of each vertex is a disjunct union of intervals on this order, of a bounded number of intervals. And this is super nice because if you have bounded continuity, then you have a simple labeling scheme. The idea is you just encode the idea is just you encode the smaller and larger vertex of each interval for each of the vertex. And then there is another part that is relatively simple, is if you take an hereditary small class, then this class has a neighborhood complexity that is not too large. And finally, the link between these two notions is quite hard, but it has been done 40 years ago by Wiesel. The idea is when you have bounded neighborhood complexity, you can find a bound on the continuity of the graph. And this is done using hypergraphs and nets, make it a bit complicated. And so there is this two steps proof. You first prove that the neighborhood complexity is small. Then you prove with Wiesel argument that continuity is small. And this gives you an adjacency labeling scheme. Unfortunately, neighborhood complexity is not small in general for factorial classes, since you could have subdivision of a clique. Okay, so this is a picture of the known result of this this field. So when you look at factorial classes, in general, you only have a lower bound of root of n. For the factorial and monotone classes, we proved previously that you can have log square of n bit labeling schemes. And on the bottom, you have what happens with small classes and small sparse classes. So this upper bound in the cube and the implicit representation for sparse classes. We will just mention three open questions. So the first is this root of n the good bound in general? The good bound in general? The second question is we prove that the neighborhood complexity is O of n log n, but we don't know if it can be O of n in general. And finally, we would like to prove that in general, the small classes actually have O of log n bit labeling scheme, even when they are not sparse. So thank you for your attention, and I wish you a good day.